As chemists, we love thinking about teeny tiny things. Really, really, really small things that are invisible to the naked eye, but give us insight into the way matter behaves, things like atoms, molecules, and ions. This second module of the course is all about our representations and descriptions of atoms, molecules, and ions, which we're going to group under the umbrella term of chemical species. Species is a term that I use sometimes almost subconsciously because it stands in for atom, molecule, or ion, and it can be used in cases and in contexts where we don't know necessarily what that relevant teeny, teeny, tiny particle could be, but we know it's one of those three, and we're interested in that thing going on at the molecular, or what we'll soon call the submicroscopic level. So we're going to start really with the atom and atomic theory, looking at some empirical observations and the natural laws derived from them that gave rise to the atomic theory. We'll talk about the tenets of that. We'll talk about the particles inside the atom, since this gives us insight into how we visualize and classify and categorize different types of atoms. Look at atomic representations, and then we'll dig into what exactly we mean by the submicroscopic model and talk a little bit about the different scales at which we think in chemistry and why it's important to think in different scales or in different types of ways that are, and the interrelations between these different types of ways of thinking. We'll introduce the periodic table and the key aspects of that from an organizational point of view, the kind of information you can get, how the elements are laid out on the periodic table, things like this. Then we'll end with a little bit of very basic nomenclature. We'll talk about how to name compounds, which are composed of multiple different types of atoms. We're not going to get too deep on this. Actually, the main point of the nomenclature discussion is why we care about nomenclature and why it works the way it does. There's a lot of arbitrariness that comes into nomenclature that you'll hear about from your professors in future chemistry courses, for example, but it's not entirely arbitrary. Actually, the structure of chemical names gives us insight into molecular structure, and I hope to make that point at the end of this module. But we're going to start with some empirical observations of the way chemical substances behave and how these gave rise to our modern conception of the way matter looks at the submicroscopic level, at the single particle level, the single defining particle level. The first natural law on this slide is the law of conservation of mass. During a chemical reaction or a chemical change, atoms are neither created nor destroyed, meaning the total mass of all substances in a chemical reaction is constant over time. Atoms don't just appear or disappear. One example of this is the burning of phosphorus in air inside a closed container. So on the left-hand side here, imagine we started with some phosphorus on a little plate or petri dish here. We've got some water down in the bottom, and we've got a glass top here that encloses the whole apparatus, and there's air inside that includes oxygen that's going to be used to burn the phosphorus. We ignite it, a chemical reaction happens, and at the end we have the product, the chemical product, which is a phosphorus oxide, P4O10. We have air that has been depleted of oxygen, since some of the oxygen has been incorporated into the product, and actually the water level has risen a little bit since there's less oxygen in the space, the headspace, above the phosphorus oxide. But notice the reading on the balance now, 937.4 grams throughout the process. Mass is neither gained nor lost overall. Things just change places, more or less. And I've already used the word atom to describe what's going on, so I've sort of already undercut myself, but this gives rise to the idea that there are these sort of immutable pieces of matter, which we now call atoms, that don't change in identity during chemical reactions. They just move around. They form different connections and things along these lines. This is the essence of the law of conservation of mass. A second natural law related to chemical substances containing multiple different types of atoms or different types of elements is the law of definite proportions. So first of all, let's recall what we mean by element and compound. So an element consists of a single type of atom, and from a sort of phenomenological point of view, an element cannot be broken down into a simpler substance. But we can take multiple elements and combine them together. The resulting substance is called a compound. Now, the essence of the law of definite proportions is that all samples of a compound contain the same proportions of the elements that constitute the compound. And so, in some sense, the ratio of the elements in a compound defines that compound. And a substance that does not have that ratio of the elements is not that compound, but might be a different compound. We'll actually come to that on the next slide. So to make this a little more concrete, let's consider the compound potassium carbonate. This is a compound composed of the elements potassium, carbon, and oxygen. And if we break down the compound to these elements and look at the masses of each type of element, we find that the ratio of the masses is 56.6, say, grams of potassium for every 8.7 grams of carbon for every 34.7 grams of oxygen by mass. Now, this is 3 different forms of potassium carbonate, maybe 3 different sources, right? All 3 of these contain potassium, carbon, and oxygen in this ratio by mass. And really, the important point of the law of definite proportions is kind of the negative of this. If we encounter a substance that does not contain, that contains, say, potassium, carbon, and oxygen, but not in this mass ratio, it is not potassium carbonate. There might be other compounds of K, C, and O. These are not potassium carbonate unless they contain this mass ratio of those 3 elements. The law of multiple proportions is a third natural law that relates to how the elements combine to form compounds. There's a bit of a setup here to understand the law of multiple proportions, but this really is a law that gives us great insight into the atomic theory and good evidence that matter is made of atoms, for reasons we'll come to after we've covered what's on the slide. So here's the basic setup. Imagine we've got 2 elements, let's say sulfur and oxygen, that are combining to make compounds. There is not just one way this can happen, is the first point to make here. The same 2 elements can combine to form different types of compounds with different mass proportions, for example. What the law of multiple proportions says is when this happens, the different proportions in which the elements combine are related by whole number ratios. They're not just random, and they don't vary continuously. We can't mix up sulfur and oxygen in any old proportion to get an arbitrary compound. In this sense, the combination of the elements is not like mixing paint colors, right? In theory, with paint, you can mix, say, red and white to get any old shade of pink that you want along an almost continuous spectrum, more or less, from entirely white to entirely red. This is not how combination of the elements works, and this is the essence of the law of multiple proportions. And to give you an example, I wanted to look at the specific example of combining sulfur and oxygen, since the mass ratios here turn out to be really nice. When we combine sulfur and oxygen, there are 3 possible compounds that we could get. And these are the oxides of sulfur, compounds that contain sulfur and oxygen. Oxide A contains sulfur and oxygen in a 2-to-1 ratio by mass. If we add a little bit more oxygen to bring this ratio up to 2-to-2 or 1-to-1 in a simplified version, we get oxide B, which again contains sulfur and oxygen in a 1-to-1 ratio by mass. If we add still more oxygen, the next oxide of sulfur, the next stable compound containing sulfur and oxygen, contains sulfur and oxygen in a 1-to-2 ratio by mass. So you can see as we go from oxide A to B to C, there's more oxygen in the compound relative to sulfur. We're increasing the amount of oxygen in the compound relative to sulfur, but not continuously, right? We have a whole number ratio between the different oxides. We're essentially doubling the amount of oxygen in going from oxide A to oxide B. And then in going from oxide B to oxide C, we're doubling this ratio again. And so there's a small whole number difference between these three oxides. And this is the essence of the law of multiple proportions. When elements combine in different proportions to make different compounds like oxides A, B, and C, they do so in such a way that the different proportions are related by small whole numbers, such as 2. What this suggests is that the elements can only combine with each other in discrete chunks, right? 1, 2, 3, 4 of these chunks can get together, and this is where these small whole number ratios come from, and really the essence of the chunk is what we now call an atom. The fundamental piece of an element is known as an atom. Now, we now know that atoms are submicroscopic chunks. These are extremely, extremely tiny pieces of matter that give rise to the identity of the elements. And the theory surrounding atoms is known as the atomic theory. There are 5 tenets to the atomic theory, and they're listed on this slide. The first tenet is that matter is composed of exceedingly small particles that we call atoms, and an atom is the smallest unit of an element that can participate in a chemical change and that really defines the element. If we break down the atom, well, first of all, the atom cannot be broken down chemically. When the atom is destroyed, we've got a completely different substance going on, and that's really the domain of physics. Tenet 2 defines the elements. Elements are composed of only one type of atom. That atom has a characteristic mass, and that mass is the same for all atoms of that element. A macroscopic sample of an element, something we can actually see, contains a huge number of atoms, all of which have identical chemical properties, meaning the properties of that one atom on some level define the properties of the element as a whole. Tenet 3 is that atoms of one element differ in their properties from atoms of all other elements. We'll start to bring this into focus as we talk about what's actually inside an atom in the next video. Tenet 4 is about compounds. Compounds consist of multiple different types of atoms from 2 or more elements. And because the atoms are combining and we can't cut an atom in half or thirds or quarters, the elements combine in small whole number ratios of atoms to get compounds that contain, for example, 1 sulfur atom and 1 oxygen atom, 1 sulfur atom and 2 oxygen atoms, 1 sulfur atom and 3 oxygen atoms, etc. And then tenet 5 is related to the law of conservation of mass. Atoms are neither created nor destroyed during chemical change. This is why mass is constant in a chemical reaction. But atoms are rearranged to yield substances different from those before the change. And we'll actually talk about what different means once we introduce representations of compounds in the form of chemical formulas. This theory is really the bedrock of chemistry, and it's really important to internalize it and make sure that everything you visualize, everything you think about as you study and practice chemistry is rooted in the atomic theory. There's a story that may or may not be apocryphal about Einstein. He was asked the question, if there's one scientific model, say we went, back to the Stone Age or had some kind of apocalypse where all scientific knowledge was wiped out except for, say, one theory or model, what would be the most important thing? Was the atomic theory. This is vital to the way we think about the material world and has been for many, many, many years. In fact, it's probably already part of the way you engage with substances in the real world. And hopefully you'll see that as we continue to deepen our study of chemistry in the ensuing modules.